Колеги, добро утро. Dear colleagues, good morning. It's maybe the most difficult session after the very nice gala dinner, but thank you for being on time. So let us start with the first keynote lecture for this morning. Professor Christoph Butenweg is the one who have to deliver it for us. Just shortly to present him. Professor Christoph Butenweg, his alma mater, as far as I know, is Technical University of Aachen, but at the moment he is a professor at Aachen University of Applied Sciences in Germany. His research areas are structural dynamic, earthquake engineering, and computational structural mechanics. He is chairman of two national code committees, Earthquake Special Task and Earthquake Safety of Masonry Structures. He is also a leader of Project Team 5, for the elaboration of Part 4 and 6 of Eurocode 8. Member of the National Code Committee 06 Masonry Structure and member of Working Group 1 Masonry Structure in TC 250. He is also member of Executive Committee of European Asian of Earthquake Engineering, member of the Executive Board Center for Wind and Earthquake Engineering at Technical University of Aachen, member of Research Advisory Board of German Committee for Masonry Construction, and more. From 2006, he is a manager of SDA Engineering, while from 2021, he is also visiting professor at the university in Belgrade. He is an author of over 250 national and international publications and 4 specialized books on structural dynamic and earthquake engineering. What is not written here, but I have to mention also, Christoph is exactly 20 years in this region. His first lectures in the frame of CE from school, doctoral school, was in 2005 in Skopje. So it's a good
long time ago.
What also I can add, he was co-advisor at least 4 candidates and influenced their research path and influenced their career. So thank you for that, Christoph, and please, the floor is yours.
Okay, so thank you, Elena, for the introduction. It's a pleasure to be here, and I would like to thank Doug for the invitation to participate to this important event here. And so I'm happy to be here. So it's more or less the Balkan region is more or less my second home. And so I'm usually visiting this region 2 or 3 times per year. So it's a long, let's say, relationship, not only to Skopje, also to other universities. Okay, but I'm not talking about the history. I'm talking about new topics today. I would like to give you a brief overview about the developments in the last, let's say, 20 years. On one hand, I will talk about the problems that we have with the design in earthquake engineering and masonry structures. And on the other hand, we have also to talk about the new requirements and demands that are coming up due to the modern architecture, due to the requirements for sustainability and so on. I will try to show you how comes it together and what are the next steps and what is needed for the future. So let's look back. So I really like to look back to the Roman times. And if we check this figure, we can see that it's very close to what we are doing today. So they also produced close to the construction site. So it was more or less sustainable. So the CO2 footprint was relatively low. And also they used earth dry masonry. So that means low energy amount. And it was already, let's say, implemented with a fire system that dries the walls and the floor. And what we also see here is that the load-bearing, let's say, system is not constituted by the masonry. It's constituted by the timber structure, and it's just infilled. So, okay, we are not facing the same problems as in the past. So we have to face much more difficult problems today. First of all, architectural demands. So if I'm looking back to the beginning of my engineering career, the structures are changed a lot. So first of all, we have openings. We have a flexible arrangement of walls. We need to have a flexibility during the lifespan of the structure. And all these things need to be implemented also for masonry structures. Second, we have a development of products. So if you compare the solid bricks from former times with the bricks that we have today, we are talking about completely two different products. One product is quite robust. The other product is highly effective for insulation. And it's highly effective, let's say, also for protecting the energy loss of the building. But on the other hand, it's probably weak with respect to the strength. So it's somehow contradictory. We have to find a compromise. We try to put everything in one product. Not sure that it is a good idea. On the other hand, we are facing problems now, especially in Germany. We are facing now problems with the production of masonry because the masonry production needs energy. So we are talking about burning temperatures of 1,200 degrees for clay bricks. So that costs a lot of energy. On one hand, that's the problem of the cost. On the other hand, the CO2 footprint is also not that good. So we have also to think about new ways how to change this. And furthermore, we have also problems with sound. So you see the void pattern here. So we are filling it up with some insulation material, but the void pattern allows the sound to propagate through the building. So that's also a problem. And then we have to do something against that. So in the end, we are asked to have also safe walls for fire protection in our residential buildings and also in multi-story buildings. So on top, during the last 5 years, it becomes more and more important. So we have this approval of sustainability. So if you would like to get financial support for your building from the state, you need to fulfill this criteria. And we are talking about flexibility, reuse, and sustainability. So because of that, we have developed new types of constructions, also for masonry. First of all, the prefabricated solutions. Second, we have also robotic solutions in the production units to be faster, and it's also a better quality. So if you are not constructing the masonry walls on the site, everyone knows it, there is a lot of impact on the human factor. We have to consider that the quality is much better. On the other hand, if we are using the products, as I shown before, we have also to think about hybrid systems for the slabs, so composite systems, in order to reduce the specific weight. And this is everything in one package. So we have, let's say, to fulfill everything together. Furthermore, we are talking about reuse, and it is a good idea to, let's say, separate the structural system and low-strength masonry. Because if we are starting to use low-strength masonry products that are much more effective in other terms, we are struggling with some problems. So it's good to have a separation. We need connections, new connections. We need also new systems. So why not using mortarless systems? So we have Lego systems now available on the German market, and also the reinforced concrete structure, for example, the frame structure, can be constituted by assembling of different elements together. So this is, let's say, the situation that we have now. And Europe is facing this problem. So there is a ongoing European Union project, like it's called Circ Boost. And you see here exactly the points that I tried to describe. Modularity, connections, and you can see we are combining steel with masonry and other materials. So hybrid structures are quite interesting, and we have to think about that. So the new solutions are already on the way. However, we have also to talk about earthquakes. So we have two problems with earthquakes. I will show you the first one. We have to distinguish between load-bearing masonry and non-load-bearing masonry, so non-structural elements. Let's start with load-bearing masonry. So what is the problem there? This is, let's say, an example. We did an evaluation of 3 modern masonry buildings in the Emilia-Romagna region after the earthquake series. So the good thing was that we had the chance to get the measured acceleration time histories close to the building site. And this project was carried out together with a group in Pavia with a lead by Professor Magenis. So the German group was calculating the buildings and the Italian group as well. It was financed by the German brick industry. So what we did is we checked the damage after the earthquake. And we saw that 2 of the buildings, there was almost no damage, no cracks, nothing. The 3rd building obtained severe damage because of deficiencies in the ground floor. So what is now the result of the design according to the Eurocodes? You can see here that both groups calculated these 3 buildings for all the events, and it was not only one event, we had also aftershocks. And the result is that we were able, both groups were able, to verify 7, 2, and 3% of the acceleration that was measured close to the building. So this is somehow contradictory, and that shows we need new design methods, and I will show you the new design method in the new generation in a couple of minutes. On the other hand, it is really the opposite. We have non-structural elements, we have infills, and we have partition walls. You can see the consequences. This is a photo from the field trip to Turkey after the last earthquake. And it is in Eskenderun. So this is a hospital. I think it was 3 years old. All infill walls, all masonry infill walls were completely destroyed. So this is a new building. But on the other hand, the structural system was pretty okay. So it's still standing. So nothing happened. The same problem we can see here for partition walls. Again, we have partition walls completely destroyed, but the structural system remains stable, at least with some nonlinearities, plastic hinges, and so on. So what is the reason for that, and what is the outcome if we design it according to the Eurocodes? Contradictory to load-bearing masonry, the Eurocode at the moment does not provide any, let's say, specific rules for the structural design and for the analysis. So the implementation is done in a really poor way. So in most of the times, we are using foam on the construction site. And because of that, the mechanical system cannot propagate. We all know that we need the arching effect. So it is really, let's say, the fact that on one hand, we cannot verify it. On the other hand, we have a problem. We do not have any rules. So what is the solution for that? We need a solution because we have also new hazard maps. I think there is a presentation about this development of the hazard maps in Europe. And it is quite clear that in some countries, like Germany, we have an increase of the seismic hazard. So we have also to handle the higher seismic loads. Okay, how can we do this? We can do this with new code. The new code is on the way. The new Eurocode will be introduced in 2028, so it's not far away. And this new Eurocode allows us to, let's say, design the structural system based on masonry in a better way. And we can utilize higher, higher reserves of the system. And on the other hand, we have new rules for non-structural elements. So if we check what are the changes, what are the important changes in the new code, we can clearly see that we have here DC1 and DC2. That means we have a higher ductility class for the structural design. We have still simplified rules, and we have new nonlinear calculation. Nonlinear calculation was not implemented quite well in the old code because the displacement capacities were missing, clear rules were missing. It was just a general procedure in an informative annex. Now it is a standard procedure, and we can apply it to all buildings. So this is really a big change. And I think we have to move forward with masonry to modern analysis and modern types of structural design. So let us check the possibilities. First of all, there's always the question, okay, this is a very simple material. It is used for hundreds of years. So we know everything. It is simple, brick by brick, in between mortar. So it cannot be that complicated. Let's try to find simple rules. In the end, or force-based design, linear force-based design, in the end, and that's what I can tell you, you are frustrated because you cannot verify it with such simplified methods. You will fail. So this is not the way that we can go in future because we have also specific products. We cannot find general rules that cover everything, that are safe enough, and that will give us, let's say, a reliability that our structures can survive in case of an earthquake. So we have to think much more about it. So the second point is we don't want to carry out nonlinear analysis in all cases. So therefore, the approach is try to increase the behavior factors in a more reasonable way. So the new behavior factor is now distinguished between three parts. First part is load redistribution. So everyone who knows the design of masonry, so it can happen in the linear design that you have one or two walls that are failing, but that are not that important for the overall capacity of the building. So then we can redistribute the forces from these two elements to the other walls, and we can still carry the vertical loads. So this is one possibility. The second part of the new behavior factor is related to dissipation of energy and displacement capacity. It's called QD. And these three types of, or these three parts of the behavior factor are given in the table. QS is the overstrength, which is almost 1 for masonry. And we can find here the new behavior factors. In the old code, it was a range between 1.5 and 2, but we ended up always with 1.5. And here we have behavior factors up to 2.8. So it looks strange in comparison to reinforced concrete, I know, but there were a lot of tests and experimental campaigns and also analysis of typical buildings in different countries that shows that we can apply such higher factors. The crucial point in masonry is the design for vertical loads. If you design the masonry building for high axial load ratios in single walls that are important to carry the horizontal load, then you are getting in problems. So the axial load ratio for the linear design is limited to 0.2. So the tests that were carried out and used are shown here. So we have the moment distribution included. We have the horizontal actuator imposing the horizontal loads. And we have the vertical pair of forces that is able to mirror the different, let's say, moment distributions with the moment distribution factor C. And then we are carrying out in a more realistic way than in the past the shear wall test with cyclic loading. So the cyclic loading tests, we have in total 350 shear wall tests all over Europe in the last 20 to 25 years. And all of these tests were evaluated with respect to the failure mode, moment distribution, axial load ratios, geometry, hysteretic behavior, and so on. So this is something that we did in the past, and this was running into the development of the code. You see 70% are related to clay bricks due to the fact that we have different void patterns on national level and on European level. Here you can see the influence of the interaction between the walls and the slab. In the past, for force-based design, we used always the cantilever system. That is not sufficient anymore. We can redistribute the forces according to frame actions within the building. And you can clearly see that the frame action depends on the length of the wall. If you have shorter walls, the walls are rotating and you can get a higher, let's say, redistribution due to the frame effect. And it depends also on the vertical load level. These influencing factors are considered now. So this is just a short video of, it's not working, it was working before. I checked it before. I will go on, it's not not a big issue. So we have here the moment distribution factor of 1.0. That's the hinge at the top. And we can clearly see that we can reach 3 centimeter, which is almost 1% of drift. And this allows us to increase the behavior factor and to use these deformation capacities in our calculations. So we were ending up with a completely new approach in comparison to the old code. In the old code, we had deformation limits for shear and bending. But to distinguish between shear and bending is very difficult because sometimes you are jumping from shear to bending because it's very close together. And then you will end up with a reduction, with a sudden reduction of the deformation capacity. Now it is a continuous approach, and you can clearly see that the psi factor is taken into account. That's the moment distribution, the aspect ratio, and the axial load ratio. So this is much better and can be easily used and implemented in all design software packages. And this allows us a more realistic calculation of the structures. And this approach was also used to derive the higher behavior factors that I showed you before. And we are distinguished between the type of masonry now, clay bricks, calcium silicate, aerated concrete. And this is also one advantage now because we have the chance, let's say, to say, okay, we have a specific material with specific properties, and we can make use of this approach for the deformation limits. And we have here the limitation of 30% in the seismic design situation, because it is assumed that in nonlinear calculation, we can take into account the redistribution also of vertical forces. So then we can carry out the calculation for each wall with respect to the changing boundary conditions during the nonlinear calculation. And in the end, we can calculate the force displacement curve for different points, considering the torsional effects. And this allows us a successful verification with a reliable basis. So this is a big change with respect to the old code. If we check the design results, we can clearly see that we are now able to withstand higher seismic actions in terms of the maximum spectral acceleration on rock. So we can rise up to 2.3, 1.9, and 3 for force-based and pushover analysis. And before, it was not possible to verify such structures. And we are now closer to the reality, also based on the fact that we compared the results with the behavior that we saw in real earthquakes. So let's talk about the non-structural elements. So one problem is solved. We have now a better design for structural elements. But what is the concept of the code for the future with the non-structural elements? And we have big changes here. We have an additional chapter, and we have to follow this chapter now. So it's not sufficient to take the foam and to fill something. So the first point is you can still use traditional infills. What does it mean? Traditional infills means that you have to insert the bricks, you have to install the bricks, you have to install the wall in close contact to the reinforced concrete frame with mortar. So this is one possibility. What does it mean as a consequence? The consequence is that you need more reinforcement, because you see there the critical region in the column and in the beams has to be enlarged over the full length. So you have to place a lot of shear reinforcement into your concrete structure, and this will lead to higher costs. Second, the limitation of the interstory drift. The interstory drift is now limited for this kind of constructions, and it will be difficult to verify it. Because if you have torsional effects, it's reduced. So due to the fact that we have an interaction of in and out of plane, it's highly reduced. So in the end, you have a solution with a higher risk, higher costs, and also more material. Because sometimes you have also to enlarge the dimensions of your columns, especially of the columns. and you cannot guarantee it. It's very difficult to control such systems. So the second option, and is shown here. So this is an arrangement of ductile infills. What does ductile mean? Ductile means that we have the possibility to insert some flexibility within the wall, and then the wall can withstand the deformation of the frame. So the pros and cons are we have a lower risk. The costs are almost the same because the installation is quite complex. And there is one, let's say, shortcoming. How can we handle openings, let's say electricity within the wall and some piping? So if you have the shear deformation, then you have also the deformation of the wall itself, and then it will harm these installations. So this is more or less the situation here. The last option is to use non-interacting infills. Non-interacting infills means that the infill is not affected by the deformation of the frame. And in this case, the design is quite simple. So you only have to verify the connection. You don't have to verify the infill itself, and you don't have to add more shear reinforcement to the structural elements. So this is really, let's say, a benefit. And on top, if you install such a solution, you have a, let's say, benefit for the sound propagation. So there are, let's say, these arguments for these solutions. But the code is open. We have 3 options, and we can make use of these 3 options, and we can use different products. So this is something that is also one step further, but it costs more work for the structural engineer. Before it was more or less, yes, let's do it, I don't know, with foam, with whatever is on the construction side. Now we have rules to verify it. This is a big difference. So I think these 2 points are more or less solved. And if we check the efficiency, I hope this is running, for partition walls. So for partition walls, it's always the problem. We have to wait for the deflections in the first weeks. Once the deflections settled up, then we can install the uppermost joint. And the problem is always to fill the joint. One solution is, for example, to use a relatively stiff element, triangle shape, and then to add the mortar from both sides. So I tried it by myself. It's very difficult without, because then you are moving the mortar from one side to the other. And especially for hollow clay bricks, because the mortar is falling into the holes. So how will you do it? So this is something that is important. If we have the videos are not working, I don't know why. Wait. I think we can run it at the end, okay? So for partition walls, we have this situation that we can reach sufficient levels of capacity by using a fully mortar joint. And this is, let's say, for example, the situation. We have a gapping, and then the compression zone will fail at a certain point. But there are also other solutions that can improve the seismic resistance and resilience, and at the same time reduce the CO2 footprint. So this is an example of a project that we carried out together with Xella in Germany, and within the ERIUS project in cooperation with the University of Bucharest and further partners. So the basic idea is to use aerated concrete and to use aerated concrete with formwork blocks. At the end of each wall, the formwork block is used as a formwork for the circular reinforced concrete columns. And we have also some additional rectangular columns. And then these columns are more or less reinforcing the walls, and they can take the tension, and we have a benefit for the structural resistance. It's quite easy to install them because it is, let's say, easy to insert the concrete there. Furthermore, we reduce the weight with slabs made of lightweight concrete and with a low content of mineralic content. And furthermore, the columns were casted with regular concrete, so because we would like to avoid the plastic hinges in the columns. So you see here the ground plan configuration, and here is the construction. So we see that we have these shear reinforcement rising up in the formwork blocks. We are filling the formwork blocks step by step. And we are installing the partition walls with the profile that I showed before. And then this structure was tested on a shaking table test. And the shaking table test is shown here. So I hope this is running. I don't know. So before it was running, maybe it would be nice to have at least this one. The video is in the same directory.
Yeah.
Let's do it at the end. Okay, now it's running. So the acceleration time histories were applied in both directions at the same time, according to artificial accelegrams, according to Eurocode 8. And here you see the acceleration up to a PGA level of 0.8 G. We obtained only minor damage up to 0.5 G, and at 0.8 G, the structural system, the reinforced concrete structural system, was highly damaged. So we obtained plastic hinges, and it was a soft story in the first floor. You can see it in the second figure here. So the upper floor was almost completely intact without cracks. And also the partition walls were not, let's say, destroyed, or they didn't show any cracks up to a level of 3G that was measured on top of the specimen. So there is a reserve because we obtained much higher values than needed for the European earthquake regions. So this is a design concept that we developed. The design concept was implemented in a software package, and also the constructive rules were defined. And now this is a chance, let's say, to enhance the seismic safety of a structure with a relatively low mass on one hand, and on the other hand, with a chance to place at critical walls these additional elements by the formwork blocks. So what should be done in future? So in Germany, we will introduce a new design code on earth masonry. Earth masonry means that we are not burning the bricks anymore. The bricks are produced in a really good quality now, and they are glued together with clay thin bed layer mortar. Clay thin bed layer mortar means that if you add water, you can completely use it again together with the brick. It is a low strength brick, but up to 2 stories, it will work. So this is really important, and this is an important step, but we have also to think about the way of constructing our structural systems for these low strength bricks. The second aspect, that's a new project, it's called flowable backfill concrete. So they started at ETH in Zurich with this topic, and we have now a project. We are using the soil on the site for producing at least non-structural internal walls by a kind of liquid concrete made of clay and soil. So this is one interesting aspect for the future, and we have to really investigate the behavior. So there is a lot of work to do. So we started with Roman times. We also have to think about new production, let's say, types with robots, and we have to carry out the production in a way that we can provide prefabricated elements with a high quality. And for that, of course, new products, new materials, we need new design concepts. So masonry is still a modern material, and you can see that it's really stable over the centuries. So here you see the Aachen Cathedral in the most affected earthquake region in Germany. It's still standing till 800. Thank you for your attention.
Christoph, thank you for, first of all, very inspiring presentation, also very informative one. So hopefully, because as you mentioned, you are very often in the region, you know that after Skopje earthquake, it seems like that our construction industry don't consider masonry as a construction material. We are struggling with that, and hopefully all these novelties in the Eurocode maybe will support this. But also what you mentioned about the novelties regarding the infill walls, I think it is even more important than that. Unfortunately, we are quite behind our time, so we will just wait a moment. Christoph, we have our president giving you some rewards. But Christoph is here whole day, so we hope to have some more discussion during the break and coffee break and lunch break. Сега продолжуваме со вториот дел од оваа прва сесија која е посветен на нашите спонзори кои помогна и овозможија да се реализира овој настан, така што во временски период од 5 минути ќе ги замолам представниците на компаниите накратко да издвојат она што сметаат дека е најважно за нивната компанија. Прво го поканувам представникот на Градежниот институт Македонија од Скопје да ги изложи своите согледувања. Дали имаме тука?
Само видео?
Само видео, во ред. Нечиста работа само видео.
Да, 9. Добре.
Визионери ја насочија моќта на своите идеи кон создавање уникатен научно-истражувачки институт и центар за знаење. Во 1975 година, оваа визија се оствари со основањето на Градежен институт Македонија. Првите проекти поставија темел за идниот развој и го дефинираа ГИМ како пионер во градежниот сектор. Од пионерство до регионален лидер, ГИМ започна значајно да влијае врз општеството преку учество во изградба на патишта, мостови и брани, кои ја зголемија поврзаноста и безбедноста. Проектите не само што ја подобрија инфраструктурата, туку и придонесоа за отворање на нови работни места и поттикнување на локалната економија. Воведувањето одржливи градежни практики значително придонесе за заштита на животната средина, намалувајќи го негативното влијание и поттикнувајќи еколошки свесен развој. Градежен институт Македонија постојано се развива за да одговори на пазарните предизвици. Со фокус на иновации и концептот се на едно место, обезбедуваме комплетни и квалитетни услуги. Инвестирајќи во најнови технологии, создаваме проекти што носат конкурентска предност и ги надминуваат очекувањата од клиентите. Присуството на пазарите во Србија, Босна и Херцеговина, Црна Гора, Албанија, Романија и Косово се зацврсти, правејќи ја компанијата препознатлив и доверлив партнер во регионот. Преку стратегијата за менаџирање со знаење, Центарот за развој на ГИМ со својот приватно научен институт ИЕГ освои престижна награда на Европската конференција за управување со знаење. Развиениот КОИН модел создаде мост помеѓу индустријата и академијата во земјите во развој, овозможувајќи трансфер на знаење и иновации кои поттикнуваат економски и технолошки напредок. Тимот на Градежен институт Македонија, составен од 350 посветени професионалци, представува најзначајниот капитал и ресурс на нашата компанија. Овие талентирани професионалци создаваат синергија и формираат динамични тимови водени од заедничка визија. Благодарение на нивната посветеност и стручност, успешно реализираме значајни инфраструктурни проекти низ државата и регионот. Движиме иновации и ја обликуваме иднината. Градежен институт Македонија гледа кон иднината со амбиција и иновација. Во новото време, фокусирани сме на усвојување на најсовремени технологии и одржливи практики. Со користење на дигитални алатки и еколошки материјали, создаваме структури кои се не само функционални, туку и енергетски ефикасни. Нашата визија вклучува развој на паметни градби и интеграција на зелени технологии, што ќе придонесе за подобрување на квалитетот на животот. Со ова пристапуваме кон градежништвото како движечка сила за позитивни промени во локалните и глобалните заедници. Од 1975 година па се до денес, ГИМ останува водечки бренд во градежништвото, посветен на квалитет, иновација и извонредност. Со 50 години искуство, компанијата продолжува да ја обликува иднината на индустријата. 50 години традиција, 50 години искуство, 50 години квалитет, 50 години извонредност во градежништвото. Градежен институт Македонија.
Како ГИМ, така и DAY3 Steel е компанија која што е редован поддржувач на нашите активности, така да предлагам представникот на DAY3 Steel да ни се придружи на говорницата.
Почитувани председавачи, почитувани професори, драги гости, ми представува особена чест и задоволство што веќе традиционално сме дел од симпозиумите на МАСЕ. Нашата соработка е плодна и се надевам дека ќе продолжи уште многу долги години. Денеска ќе ги искористам овие 5 минути не за да ги презентирам производите на DAY3 Steel и на групацијата Сиденор, за кои што знам дека за повеќето од вас се добро познати, туку сакам да изразам голема благодарност и признание на Градежниот факултет Скопје, Друштвото на градежни конструктори на Македонија, Институтот за стандардизација на Република Македонија, ИЗИС, ГИМ, Сдруженијето на градежништво при Стопанската комора на Македонија и Царинската управа. Имено ние пред 10 години, може и повеќе, започнавме една макотрапна заедничка работа да воведеме ред во хаосот кој што владееше со пазарот на градежни материјали, особено во пазарот на бетонското железо. Немаше никаква контрола на тоа што кој што увезува, од каде увезува и со каков квалитет увезува. Само Господ знае каков квалитет на град би се изградија во тој период и кој живее таму и колку се тие добри. Знаете дека имаше еден период кога една компанија во Албанија нудеше, и тоа на големо, и го промовираше лесно железо. Тоа лесно железо беше тешка измама. 10-ката, 9-ка, 12-ката, 11-ка и така натаму. Направивме многу симпозиуми, конференции, состаноци и конечно можем да кажам дека најпрво се разбира беше донесен македонскиот стандард МКС 1021, кој што одлежа во ФИОКа во Министерство еден извесен период пред да биде потпишан. Потоа беше донесен и Законот за градежни материјали и тој одлежа еден период во ФИОКа. И конечно кога беше донесен Законот за градежни материјали, ние веднаш целата групација, сите наши фабрики ги сертифициравме во ГИМ според тој закон и бевме единствени сертифицирани на овој пазар 3 или 4 години, знаат од ГИМ. Среќен сум да кажам дека од почетокот на оваа година конечно Царинска управа ги затвори границите, пазарна инспекција направи огромна контрола и сега на овој пазар конечно имаме сертифицирано железо кој е по македонските стандарди, кој што има проверено потекло и проверен квалитет. Макотрапна работа, заедничка работа и сакам да нагласам дека можеби и ово е единствениот начин на кој што можеме да направиме промени. Приватниот сектор и вие како наука и како институции За крај само уште еднаш дозволете ми благодарност до Градежен факултет Скопје, Друштвото на градежни конструктори на Македонија, Институтот за стандардизација на Република Македонија, ИЗИС, ГИМ, Сдружение на градежништво при Стопанската комора на Македонија и Царинска управа. Ви благодарам на сите.
Благодарам за истакнувањето на овие значајни придобивки во нашата индустрија. Во право сте, долги години за тоа се разговараше. Одлично е што имаме ваква информација. Сега можност има да ни се представи ЕПТИСа Шпанија, регионалната канцеларија за Југоисточна Европа. Please, the floor is yours.
Hello, this is Juan Manuel Garcia. I'm civil engineering, I'm a structural engineer. I am director of instrumentation and control area in EPTISA, and I'm going to give you a brief presentation of our company. So, who we are? We are an engineering consultancy and technology company with more than 70 years of experience. We have presence in more than 40 countries. We are a group of great professionals, more than 1,000, and we have nowadays ongoing projects around 300. So our activity is mainly, we started in Spain. Our activity is, or 40% is in Spain, but we have moved in the last years also in the rest of Europe, and we have also presence in America, Africa, and Asia. You can see here all the countries where we are working, and where are our offices and delegations. It's good to know that we have our offices here in Macedonia and also in the region, in Belgrade, Bosnia, and Croatia, and so on. And this is our areas where we are working. In infrastructures, we are in transport sector, roadways, railways. In water, all the water cycle, from dams to network water treatment plants, and so on. We provide ground engineering services. In energy and industry, we work in renewables, conventional, oil and gas, and also work in the industry and do environment services. In buildings, we were working in commercial, industrial, and institutional. We provide consultancy services in public policy development, also circular economy, digital sustainability and climate change, also mobility. Provide quality control services with European standards and accreditations. And we also provide structural health monitoring services in structures, dams, tunnels, and so on. We provide for our clients this kind of services from the conceptual phase, design and pre-construction, during construction, and all post-construction services during operation and maintenance. So, and what we have many projects to explain here, but we only have one more minute. We are in all colleagues, structural engineers, so I think that these both projects could be of your interest. We have worked in the new Real Madrid Stadium in Madrid. We have provide services during the new cover and the new structure in I know how to say sorry. When we need to remove the grass in the, downstairs, and also this kind of bridge health monitoring system that we provide in bridges, in the railways, and in we will see posters this afternoon. So that is all. This is our time. So thank you.
Поканувам доколку е присутен представник на Институтот за сизмички отпорни градби и климатски промени од Скопје да се обрати. Ако не, следни кои што не поддржаа се Масон инженеринг од Скопје. Дали има представник? Во тој случај Пејко, представник на Пејко од Финска, може да ги сподели нивните искуства. Изволите.
Good morning, ladies and gentlemen. My name is Zsolt Kokrel. I'm the contact for all of engineers and contractors for Balkan region. If you have some projects and needs for Payco solutions, you are free to contact me. Payco is a Finnish-based company. We this year celebrating 60 years of being on the construction market with innovations and widely accepted solutions. As you can see this map, we are working all around the world, mostly in Europe, but in Asia, America, and Austria we have offices. We are manufacturing in-house, means that all of our products are produced in-house, not outsourcing. We have teams in 30 countries. Local language support you will have for all of these regions. And we have globally over 2,000 employees. We are working with construction companies, supporting with technical details and supplying them with our products, working with investors in stage of development of projects, working with designers to find the best solution for their needs. And the biggest part of our work is with precast concrete factories providing the connections. The Payco is synonym for connecting concrete, means connecting cast in situ concrete with precast concrete, cast in situ concrete with also cast in situ, and connecting prefabricated elements together means like column extension, on one column on top of another column, and we can also provide connection between concrete and steel structure. We have design tools. It's free to download and use it. Drafting tools, installation instructions, technical manuals, and also all products are available to insert in the designs. This slide is also mentioned. We have our own production in our factories, not outsourcing. And that is very shortly from Payco. If you have some question or have some technical detail to solve, you can freely contact me, or you can type on internet payco.mk and you will find my contacts. Thank you for attention.
Thank you for this nice and although short but nice presentation. And with this, we finish the second part of this session, and we can continue with the third one, which is actually presenting the accepted papers. We have 4 attractive topics. So the first one to be presented is a topic, Enhanced Seismic Safety of Masonry Infill Reinforced Concrete Frame Structures in all these connections. And I suppose Marco is the one who will present it. Marco, please.
Sure. Okay. Hello, everyone. Thanks for the introduction. I have a pleasure to present you, let's say, some parts of our work that comes from almost 12 years of working on the topic of masonry infills. And here you'll see, let's say, latest findings that we have to present. So regarding the masonry infills, you all know the status. We have the reinforced concrete structure that is, let's say, carrying the load. It can stand by itself. And then we have masonry infill walls, who are often used all over the world, but they are considered as non-structural elements, which is true for the gravity load. But when the earthquake comes, then they are getting activated. They're changing the stiffness of structure, dynamic characteristics, and thus the earthquake loads acting on it. However, we are mostly neglecting them in the design, which is, if they are done in a traditional way with the mortar and rigid connection, it's unjustified. And then we have a lot of issues with the structure itself, but also with the infills getting damaged. And sometimes even the whole structures can get damaged because of the interaction with this non-structural element that we, let's say, do not take into account. And here I selected several earthquakes from the last 15 years. Here's from Italy, and maybe you can pay attention to the magnitudes that I selected. So there are different levels of magnitude, but you can see always more or less the same pattern. The infills are getting damaged, falling in out of plane, collapsed, and then jeopardizing first the people inside and outside of the buildings, trying to maybe escape from the buildings, but additionally also jeopardizing the let's say, things that are around the buildings, like here in Spain, the cars. These are the photos from Albania, from our reconnaissance mission after the earthquake, all the buildings. So there were a lot of, let's say, light damaged buildings structurally, but heavily damaged in a non-structural way regarding the masonry infills. And this is one interesting example that I like to mention. It is the earthquake that was kind of in the shadow of the big one that we all know from the February 2023 from the Turkey. This one was 3 months before in Dusce, and it had really light damage to the structural elements, usually only because of the interaction with the infill and then the short column effect, but infills were heavily damaged. So a lot of costs and issues related to the infills. And then we come to the one that we all know, and I like to point out to the scenes that we saw. So beside these infills damage, also you can see the buildings that were standing, kept standing, that structural elements were not damaged or maybe lightly damaged. All the infills were cracked or collapsed in out of plane. And here is the pattern that I would like to point out. You can see that all the infills collapsed in out of plane in the lower stories. Usually we would expect this would happen at the higher stories because the acceleration raises up with the amplification in the higher stories, but the out of plane that is acting perpendicular to the walls was pushing them out in the lower stories because of the interaction with the in-plane. And this is important effect to take into account. So the infills are getting cracked or detached from the reinforced concrete frame because of the in-plane deformation, which is the highest in the lower stories. And then you don't need too much to push them in out of plane. Even this lowest out of plane that is lower to, and at the lower stories is pushing them out. And here is, let's say, one a graph or one photos to show it. So these places, when the frame deforms, these corners are vulnerable places because there's no more contact between the infill and the wall, and then the wall easily falls in out of plane because there's no more stable statical system. So there's no boundary condition that holds the infill inside. And you can easily see it also by the contact areas marked with the red in these graphs. So due to the in-plane, the contact area is reduced to the, let's say, diagonal direction. Then when you add the out-of-plane, it's even more reduced. And then as a result, we have really small areas of contact, and that's not enough to hold the wall to fall in out-of-plane. So this is important aspect that I will come to the point. And then we were thinking, okay, what should be done? Usually, the idea is to strengthen it, to add some steel, mesh, anchors on. That doesn't work. We tested it. It doesn't work. It doesn't solve all these issues that we mentioned. Sometimes even makes it worse. Then we said, okay, let's make it a real non-structural element, decouple it from the frame, place some soft material, and we decided to place the rubber around. But the crucial point of this system, of this connection that we called INODIS, is that the rubber is placed on all four sides, and it's divided in 3 strips. Middle strip is always connected with the mortar. Mortar is usual connection. So middle rubber strip is connected to the concrete elements, and 2 outer strips are connected to the bricks or to the wall. In this way, you have here, let's say, simple animation that I made. It's a horizontal cross section, so the columns, wall, and 3 strips. And then when the earthquake comes from the left to the right, you have here the compression of the rubber that is isolating the infill. It's not transferring the load to the infill. It's not activating infill and not damaging it. On the right side, you have always this shear key connection of these 3 strips that is holding the wall continuously in the height and the length, not to fall in out-of-plane. The same happens in the other direction. So we are avoiding difficult installation of anchors that are, by the way, not working because they are producing the stress concentration in the bricks and they cannot hold the wall in out-of-plane. In this way, in one connection, we are decoupling it in in-plane and then holding it in out-of-plane and solving both issues. So this is how this looks like. It's made out of shredded old tires. Therefore, it's quite, let's say, cheap or cost affordable. And furthermore, these shredded parts are binded together, and they made strips of recycled rubber components that are quite porous. Maybe you can see it on that photo there in the corner. And then the connection with the mortar is really good because it penetrates to the rubber and then also has good connection to the wall and to the concrete as well. So these are the construction steps. So you first place the middle strip at concrete elements. Then you place the outer strip, put the mortar on them, and then the bricking up is usual. You just are placing the mortar to the outer strip rubbers, not to the concrete, which was to the column that was traditional way. And then the bricking up is usual. And the best part is the top. The top joint is usually the most painful for the workers because to fill a 20-25 centimeter brick thick wall is really painful and time consuming. Here we have already the middle strip glued. You have the top joint, and then you take the piece of rubber that is 1.2 meter long, you put the mortar in it, and then you slide it in. If the joint is slightly thicker, you just place more mortar, slide it, and let's say the more amount of mortar will be left out, and then you close up the joint completely, and you have secure boundary condition, and of course also the acoustic isolation is better. What we did a big campaign of tests on 9 traditional and 9 with this INODIS connection with windows, doors, combined in-plane, out-of-plane tests. And here I will show just some of them. Here is the summary that shows the video. On the left one, you can see the traditional specimen. On the right, the specimen with the INODIS connection, with the DAC system showing cracks already at the low level of drifts in plane in the traditional system, and pushing it in out-of-plane. So this test, we applied airbags, surface pressure in out-of-plane, and then at the same time simultaneously in-plane, in this way simulating the action of earthquake in in-plane and out-of-plane at the same time. And then you can see on the right the specimen, so everything is absorbed in the rubber, and there is no damage up to 2.4% of drift, something like that, when the rubber is getting compressed, and then the infill is getting activated, and then the cracks can appear in the specimen. Then we did one big, nice project here at Isis Lab. It's called within the Areas project, or FlareJoy project it was called. We applied on this, let's say, small box, or in full scale, 3 by 3 meter was mostly, let's say, the distance and height of the columns and the distance between them. And here's the video where we applied the acceleration. It is unidirectional shaking table. So first we applied it in different percent level in one direction, no damage at all. Then we lifted up with the crane, rotated, and applied it again. In that way, we tested the walls that were first tested in plane, then were subjected to the out of plane load, and that was sequential test in both in plane and out of plane, reaching no damage in the walls. Important to mention that we figure out from not just our testing base, but from others. So there is idea of some colleagues that infills are not changing so much the stiffness just in the beginning, and then soon they get cracked and then you can disregard them. That's not true. So you can see, for example, at 1% of drift, there is still 3 times more stiffer infill frame than the bare frame itself. That means that the period is 60%. That means that if you calculate it with the bare frame period, which we are usually doing, you are underestimating the load level, seismic load level on the structure itself. And then we did the design of the infills according to the current Eurocode, which is demanding to take into account this interaction between the infill wall and the column. And of course, in the second generation, this is even more better defined. You have even to verify the infills itself, the strut force in the model. You have to model it. You have to take lower Q factors for the rigidly attached infills, but for the decoupled ones, higher ductility is allowed. So Q factor 2% of inter-story drift. There is no strut force verification, no interaction, because this rubber is eliminating the interaction. Therefore, you can continue modeling it with the bare frame structure. The only thing that you have to do is to assign enough thickness of the rubber to accommodate the inter-story drift displacement. There is one simple equation in the code. Here is a summary of my last slides. We did the comparison on the 6-story building, the real one, comparison of design with in-notice connection without, and of course without in the rigidly connected infills you get much more reinforcement and concrete. And then when you calculate it with the costs, it turns out that you are saving so much in the cost that you can pay for this connection and still save the money in the amount of reinforcement and concrete that you saved. Of course, since we are spending less CO2, less reinforcement and concrete, then we are also saving CO2 for the structure itself. So to summarize, traditional infills are getting damage at very low in-plane drifts. We proved it with a long, several years campaign that you can easily reach more than 2% without any damage to the infills. That means that you have now to define your reinforced concrete structure well, but the infill is not making any problem to you as it was done so far. And there is this prevention of stress concentration and interaction. You're solving it in in-plane and in out-of-plane. And the design is simple, straightforward, and reliable. And also the system, as you can see, it's used with a mortar, so therefore it can be applied to any types of the bricks. So these are the institutions and project grants in this 12-year period that we got support from them, and we are very thankful. Thank you.
Thank you, Marco. It was obviously very nice continuation of the presentation of Christoph. So one very important problem that we have and discuss it so many years, it seems like you suggest us very good solution. Dear colleagues, due to the time limitation, we think that it will be better if we continue with the next presentation and the discussion to keep it maybe at the end of the session, depending on the time. Thank you, Marco.
Добро, почитувани колеги, продолжуваме понатаму, значи се уште сме во областа на очигледно на овие преградни зидови. Така да следната презентација е од Илјана Мијалкова, Александар Богдановиќ, Марко Маринковиќ, Енрико Тубалди и Бартоломео Панто, со наслов Analytical Approach to Seismic Behavior Assessment of RC Frame Structures with Rubber Jointed Masonry Infill. Илјана, повели.
Hello, everyone. Thank you, Professor Veronica. I would like to make a continuation to Professor Marko Marinkovic's presentation and represent to you part of my doctoral dissertation, which is analytical approach to seismic behavior assessment of those type of structures that Professor Marko was discussing. As we can see from this slide, we have the most common type of structure that we have in most seismic-prone regions of the world. That is the reinforced concrete structures with masonry infills. What happens when we place masonry infills inside the reinforced concrete was already presented by Professor Marko. I can only just say that we can see the time acceleration diagram above these three types of structures, above the basic bare RC frame, above the infilled RC frame, and the isolated infilled RC frame. And what I can say is that these infills significantly alter the dynamic characteristics of the building. They can make the acceleration higher, make it more peak, and also shorten the vibration period. And what we can do to calm the storm at this small range of drifts is we can strategically place rubber joints between the frame and the infill and isolate it from the earthquake actions on the infills. I have decided to continue with macro modeling strategy for my doctoral dissertation, and I have selected a discrete macro element method. This is an element that was originally developed by Professor Bartolomeo Panto. It was originally invented for assessment of old masonry bearing buildings. However, through the years, it has evolved, and now we have improved it to be efficient element for simulation of complex in-plane seismic response of masonry infills, and it can also be applied to traditional infills as well as isolated infills. This element is implemented in OpenSys finite element software framework, so it is open to all contributors. The key components to these elements are the articulated quadrilateral panel, which represents the masonry panel. We have a single one-dimensional diagonal link within the panel, and we have 8 two-dimensional nodal connections or perimetral contact links that connect the masonry with the adjacent structural components. I would like to say a few words regarding all components. First, we have the articulated quadrilateral panel, which you can see on the left. It is consisted of 4 rigid linear elements and 4 vertices, and within its inside there is a single one-dimensional link. This duo was specifically designed to capture the masonry's shear behavior and also its associated failure mechanisms. So, independent from the outside connections, it only represents the diagonal shear behavior of the infill. The diagonal link is modeled through the pinching for material, which can be seen on the lower right part of the slide. This material is consisted of a quadrilinear envelope curve. It has a pinching effect and degradation of reloading stiffness and strength, which is important to capture the complex masonry behavior. And also once again to note that this one-dimensional diagonal link is independent of the outside normal loads and is strictly inherits the shear properties of the masonry. We continue with the two-dimensional contact links. The mechanical scheme of these contact links is represented on the left slide. It is basically a zero-length element modeled in OpenSys that has normal and tangential spring, and it has also rigid offset, so it can be strategically attached to the adjacent frame. It is divided in normal response and tangential response. The normal response would represent the masonry axial and bending behavior and is modeled through the concrete 02 material model, which is available in OpenSys as a readily available material model. This is a good representation because it can represent both in compression and in attention, and also can show the degradation and of the stiffness and the softening of the element. Then we have the tangential response. This has it is two-folded. First, it can represent the sliding motion and mortar joints. If we separate the macro element into more mesh, into a smaller mesh, or it can represent the interaction between the infill and the frame interface, which is very important, as Professor Marko Marinkovic noted. Key parameters for this tangential response include cohesion and friction of the joints, and for this study, they are adopted as constants. So there have been several case studies that were investigated. Two of them will be presented here that were regarding cyclic analysis, experimentals with cyclic loading. The first one is a case study of traditional infill frames that was tested at the University of Ljubljana. And there was an ongoing investigation of the seismic response of full-scale reinforced concrete frames with traditionally constructed masonry infill. And the second case study is the INODIS case study, which was presented by Professor Marko, which is the investigation of seismic response of full-scale RC frames with decoupled masonry infill. Both of them were numerically calculated using the discrete macro element method in OpenSys. Regarding the first case study, on the left, you can see the setup of the experiment. It is a usual reinforced concrete 1x1 height frame that is designed by Eurocodes, and we have a traditional infill wall connected traditionally with mortar joints at its edges. On the right, there are two tables that represent some of the characteristics that were material characteristics that were used in OpenSys. We can see on the upper table masonry characteristics for the normal contact links, which represents material behavior in horizontal and vertical direction. And on the lower right table, we can see the contact link parameters that are describing the frame infill interaction. So we have the stiffness of the joints, which is very high due to the traditionally constructed manner. We have cohesion parameters that were taken from literature as for similar projects. And we have the friction parameters that you can see are very high, that are contributing to the infill interaction with the frame. So using this discrete macro element and using a single discrete macro element, a cyclic analysis was performed in OpenSys. And with the blue curves, you can see the obtained results from OpenSys cyclic analysis. I would say that this element, having in mind that it is a macro element and a single element, provides very satisfactory accuracy. Also having in mind that masonry is not really a homogeneous material, and also having in mind the setup of the experiment. However, one must note that it does give a slightly higher base shear values regarding to the experiment, but this is mainly due to the nature of the concrete 02 material model that is implemented in OpenSys, where the initial stiffness of the material is already predetermined by an equation. The next case study is for the decoupled or the isolated infill frame system. This on the left, we have the setup of the experiment. We can see that between the reinforced concrete elements and the masonry infill are strategically placed rubber strips, elastomeric rubber strips. The strip at the bottom and the top are with much higher stiffness and smaller thickness, and the strips on the vertical sides to the columns are much less stiffer, they're much softer, and they also can have varying thickness depending on the relative or the local conditions and the necessary relative displacement. For discretional purposes, I only place the contact link parameters in share that are describing the frame infill interaction. You can see that the stiffness of the joints are drastically smaller than the ones in traditional infilled frames, much smaller. The cohesion parameter, due to the sliding interfaces here, is taken to be 0. And we have low friction interfaces with 0.15 and 0.35 for the horizontal and the vertical joints. What I would also like to note is that in these isolated frame systems, the decoupling joints are working as a mechanical system in series. And this is what actually softens the system because we have now a series of a masonry panel and a rubber strip. I know all this was explained by Professor Marco, but here now we have numerically supported evidence. As in the previous case study, cyclic analysis was performed using, again, a single macro element model. And these are the results that I have obtained from the analysis versus the experiment. We can see that there is no more sharp decline of strength, that this low in-plane drift that is now overcome. And we have up to 4 times, I think, higher in-plane capacity drift. Again, we can see that within the smaller range of drifts, there is a little bit of a higher base shear, an overestimation. And this is again due to the nature of the concrete 02 material. But what is very important, and the most important, is that we have a similarity to the ductile reinforced concrete frame. We can see that within this hysteresis. And it is something that can be performed in future and in the present to mitigate the risks that carry the traditional infill frame, to protect the infill from preterm damage, because we know that it can damage even with moderate earthquake intensity, and it can pose risk not just to the structure, but also to the occupants, to the goods inside the structure, and even for the outside of the building people. As conclusions, I can say that this element, having in mind that it is a macro element, has satisfactory accuracy to capture the complex hysteretic behavior, mainly due to the very cleverly divided parts of it, which can capture the non-homogeneity of masonry. We can confirm that the strategic implementation of rubber joints effectively mitigates the detrimental effect of the brittleness of the masonry. I also already noted the tendency to slightly overestimate the stiffness. This can be a step for further improvement. And of course, the next step involves extending this analysis to real earthquake input records, which is already in progress for the ARES project that was and the experiment that was conducted in ISIS. Thank you very much.
Благодарам, Лиљана, и навистина пофалби за вклучувањето нови модели и OpenSys софтверите во една вака успешна аналитичка верификација на многу комплексното состојбите кај зидајата. Благодарам уште еднаш. Преминуваме понатаму. Наред презентацијата со наслов Експериментално испитување на екзоскелетен систем за интегрирано конструктивно и енергетско зракнување на армирано бетонски конструкции од нашиот млад докторант Антонио Шокларовски и група автори во рамки на проектот ARES. Повели, Антонио.
Ви благодарам, професорке, почитувана публико, почитувани колеги. Мојата денешна презентација се однесува на едно експериментално испитување на екзоскелетон системи кои пак представуваат интегриран пристап, односно интегриран начин на конструктивно и енергетско зајакнување на објектите. Мојата презентација е поделена во 6 делови, односно најпрво ќе започнам со воведен дел, потоа ќе да кажам збор два за интегрираниот пристап за зајакнување на објектите, а потоа ќе се префрлам на експерименталното испитување реализирано во лабораторијата во Институтот за земјотресно инженерство и инженерска сизмологија. Градежниот сектор денес се соочува со големи промени за разлика од минатото, односно, како што знаеме, постојаното градење на нови објекти не е толку атрактивно, бидејќи имаме потреба од зајакнување на веќе постоечкиот градежен фонд. Тоа е резултат на големите климатски промени, зголемените ризици од природни катастрофи, како и намалувањето на негативното влијание кон животната средина. Знаеме дека како во Македонија, така и во поголемиот дел од Европа, градежниот фонд е изграден пред воведување на сизмичките кодови, односно истите се проектирани само на вертикални товари, па како резултат на тоа неопходна е нивна реконструкција, но покрај сизмичката слабост на објектите имаме и голем дел од објектите се енергетски неефикасни, односно самите трошоци кои произлегуваат од нивно ладење и греење се многу големи и емисијата на стакленички гасови исто така доста голема. Градежниот сектор е одговорен дури за 35% од загубата односно од потрошувачката на енергијата и дури до 40% од емисијата на стакленички гасови. Како резултат на тоа, низ Европа, а и низ светот, низ големите земји во светот се воведуваат голем број на регулативи и политики со кои би се намалиле тие ефекти, односно да се зголеми енергетската ефикасност на објектите, а воедно и да се зголеми носивоста на истите, односно конструктивната носивост на истите. Тука би ги набрал European Green Deal, исто така Nearly Zero Energy Building, кој е воведен во Кина, во Индија имаме голема стапка на пораст на населението и зголемување на градежниот фонд, па неопходно беше воведување на некаква регулатива. Исто така се работи на такви регулативи слични во Америка и во Велика Британија. Сега, зошто интегриран пристап, бидејќи со еден зафат се покриваат и конструктивно зајакнување на самиот објект и добивање на поенергетски ефикасни објекти, а воедно ќе се подобри архитектонскиот изглед и нема да се наруши функционалноста на истиот. Како едно иновативно и ново решение, која ги опфаќа претходно споменатите предности, се екзоскелетон системите. Екзоскелетон системите се конструктивни единици кои се поставуваат до објектот и се прицврстуваат за истиот. Тие можат да бидат градени од најразлични материјали со најразлични геометриски карактеристики, да бидат поставени до објектот на различни диспозиции или да се опшијат околу целиот објект. Како резултат на тоа произлезе идејата за делот ARIES проектот, односно ARIES Resume, кој под водство на професор Антонио Формисано од Универзитетот во Наполи. Како резултат на тоа се изградени два објекти, армирано-бетонски конструкции со прегнани ѕидови од чуплива тула, кои се карактеристични за објекти кои не се проектирани по сизмички кодови, односно се проектирани само за вертикални товари. Двата модели се направени идентични. Разликата меѓу нив е во текот, ќе ви презентирам од наредните слайдови, дека времето, односно позицијата на екзоскелетон системот е различна. Во однос на екзоскелетон системот, тука е избран екзоскелетон систем со лепено ламелирано дрво, кое помеѓу себе е поврзано со челични капи, на кои пак се прикачуваат на самиот објект. На профилите на елементите од лепено ламелирано дрво се прицврстени челични профили на кои е прицврстен алуминимскиот панел и дрвената плута која служи за добивање на енергетска ефикасност на самиот објект. Значи, постапката за поставување, односно инсталирање на екзоскелетон систем е доста едноставна, односно во првата фаза се поставуваат пинови во зглобовите на армирано-бетонската конструкција, потоа на истата се прикачуваат дрвените елементи на кои се прецврстени челичните профили и потоа само се поставуваат алуминимскиот лим и плутата. Експерименталното испитување беше реализирано во 3 фази, односно првиот модел беше испитуван во 2 фази. Првата фаза е модел без екзоскелетон систем, односно е испитуван до постигнување на одредени оштетувања на истиот, потоа истиот е реконструиран со екзоскелетон систем и така е добиена втората фаза, а во третата фаза е испитуван вториот модел кој пред негово тестирање беше инсталиран екзоскелетон системот. Во поглед на инструментација користени се акселерометри, мерни траки, мерачи на поместување помеѓу зглобовите и апсолутни поместувања на самиот систем. Во однос на влезната побуда избрани се 3 различни влезни побуди, односно 2 од случајни земјотреси, Адана и Умбрија, и еден синтетички генериран земјотрес според Еврокод 8. Првата фаза, како што може да видите, направени се 19 тестови. Дел се за добивање на динамички карактеристики на објектот, потоа се направени иницијални тестови со мали интензитет од 3 записи, па потоа е избран еден од тие 3 земјотреси, односно синтетички генерираниот, за да во текот на тестирањето се зголемува неговиот интензитет се до добивање на посакуваната цел, односно во првата фаза до добивање на оштетување на системот. Како што може да видите од видеото, во првата фаза имавме доста големи оштетувања, како на конструктивните, така и на неконструктивните елементи. Имавме колапс на ѕидовите од приземното ниво и имаше доста големи оштетувања на конструктивните елементи. Во втората фаза беше инсталиран екзоскелетон системот на таа конструкција и беше повторена истата шема на тестирање, односно истите интензитети на земјотреси беа аплицирани во оваа фаза, со тоа што имавме плюс 3 чекори, бидејќи капацитетот на конструкцијата ни го дозволуваше тоа. Доколку се споредат првите 2 фази, на диаграмот се прикажани поместувањата, односно дрифтот на самата конструкција, може да се забележи дека на последниот тест имаме големо покачување на поместувањата на дрифтот како резултат на големите оштетувања на конструкцијата, додека во втората фаза, каде истиот е реконструиран, имаме една крива која ни покажува благо покачување на поместувањата во однос на интензитетот и немаме нагли пореметувања на истите. Третата фаза се однесува на тестирање на вториот модел, кој претходно не беше оштетен, односно беше нов. Во оваа фаза се направија најголем број на испитувања, со тоа што се стигна дури до 200% од записот кој беше задан и поради достигнување на лимитот на сизмичката платформа беа направени дополнителни рандом тестови со тоа што беше побудена конструкцијата во резонантната фреквенција и беа добиени најголемите поместувања. Во третата фаза имавме оштетување на преградните ѕидови, но тие се појавија дури на последниот тест каде имавме забрзување од 1G. Нереално за случување во природни услови. Доколку ги споредиме трите фази, односно деградацијата на крутоста после секој сизмички тест, може да се види дека Во првата фаза имаме нагло опаѓање на фреквенцијата после секој сизмички тест, додека во втората фаза, после реконструкција, имаме дури 3 до 4 пати зголемување на фреквенцијата со самото поместување на екзоскелетон системот и линијата, односно кривата, благо опаѓа согласно во тек на тестовите. Исто така во третата фаза имаме највисока фреквенција, логично бидејќи објектот не е воопшто оштетен, и исто така линијата таму може да се забележи дека благо опаѓа, нема нагли пореметувања. На крајот би завршил со неколку заклучоци, односно од ова експериментално испитување се покажа дека доста се зголемува сизмичката отпорност на конструкцијата доколку се постави екзоскелетон системот, и исто така добивме информација дека е добро решение за реконструкција на веќе оштетени објекти. Истите екзоскелетон системи се доста истрајни и даваат интегритет на конструкцијата. Не споменав претходно, покрај задржување на конструкцијата како целина и да се случат оштетувања, немаме колапс на надвор, туку имаме навнатре, што до некаде е добро. Доколку се направи споредба на трите фази, може да се заклучи дека првата фаза, односно инсталирањето на екзоскелетон системот пред пуштање во употреба на објектот, има најмногу поволности, односно најповеќе позитивни страни. И последно, но не најмалце важно, односно најмногу важно за популацијата која не е од инженерската фела, е дека лесно се инсталираат и се мултифункционални, односно се добиваат повеќе предности со еден зафат. Ви благодарам.
Благодарам, Антонио, и честитки на вистина до тебе и целиот тим за вака успешно реализирана експериментална програма, значи комплексна и успешно реализирана. Овие интегрирани решенија не се нова идеја, меѓутоа секој нов, да кажеме, начин или систем што ќе се особено што ќе се потврди со експерименталната испитување, е секако добре дојден. Се надевам да продолжуваш по овој пати во завршувањето на докторските студии и успешно завршување на проектот Series, односно Aries. Се извинувам. Добро, продолжуваме понатаму со последната презентација. Исто имаме млад докторант, Маја Гошева, Александра Богдановиќ, Зоран Ракичевиќ и Кристијан Мајнхарт, а насловот е Нумеричко моделирање на герб вискозните зидни придушувачи со експоненционалниот Максвелов модел. Повели, Маја.
Добар ден на сите. Денес ќе ви представам дел од мојата докторска работа за нумеричка анализа на вискозни зидни придушувачи со помош на експоненцијалниот Максвелов модел. Во оваа презентација ќе објаснам кратко за овој придушувач. Ќе зборувам конкретно за герб вискозниот зиден придушувач, кој што јас го работам. Ќе го објаснам експоненцијалниот Максвелов модел и пресметките на параметрите на овој модел, кој што се суштинска работа за целата оваа нумеричка анализа. И на крај ќе направам споредба на резултатите добиени од нумеричката анализа со експерименталните тестови. Овде на сликата можете да видите како изгледа овој придушувач. Се состои од челичен сад, кој што внатре е исполнет со вискозна течност. Овој сад е прицврстен за долната плоча, а во садот плива челична плоча која што е прицврстена за гредата на горниот кат. Со секое релативно движење на долниот кат во однос на горниот, настанува движење на плочата во тој сад и со движењето на плочата во однос на таа вискозна течност што ја има во садот, настанува триење и со тоа се пригушува енергијата од тоа движење. Вискозниот зиден придушувач што јас го работам е направен од компанијата GERB во Германија, која што произведува направи за контролирање на вибрации, и тие имаат изработено два типа на ваков придушувач, и тоа со една плоча, single vein damper, и со две плочи, double vein damper. Овде можат да се видат димензиите на дамперот, висината и ширината е еднаква, се разликуваат само во дебелината и во тежината на самиот дампер. И исто така компанијата GERB ги има направено експерименталните тестови на овие дампери. Ова се информации од тие тестови, 8 по број, каде што варира фреквенцијата и амплитудата на поместување. Максвеловиот модел е многу едноставен модел. Единствено сложената работа во овој модел е тоа што е експоненцијален модел, и многу е важен одбирот на податоци, затоа што со мала промена ќе има голема разлика во резултатите што се добиваат. Тој се состои од линеарна пружина со крутост К и експоненцијалниот придушувач со коефициент на придушување С и експонент на брзината на придушување алфа. Силата во дамперот е прикажана со равенката. За пресметка на овие податоци, на параметрите на овој модел, поради нивната експоненцијална зависност, имам направено сооднос на параметрите, кои што ги имам пресметано за сите тестови поединачно, и како средна вредност за експонентот на брзината на придушување ми е излезено 0,55, и според таа експоненцијална, според зависноста на алфа и С од овие графици, може да се увиди дека коефициентот на придушување за дамперот со една плоча е 2000, а додека за дамперот со две плочи излегува 4000, што е исто така многу значаен фактор дека податоците се соодветни, поради тоа што крутоста соодветно одговара од една плоча и дупло со две плочи, како коефициентот од 2000 до 4000. Нумеричкиот модел за мене конкретно ми е направен во софтверот SAP со користење на нелинеарен линк елемент, и од заграничните услови на овој нумерички модел, во јазолот 1 е вклештен, а додека јазолот 2 е слободен, освен се спречени само поместувањата во хоризонтален правец, и исто така во овој јазол се нанесени поместувањата, историјата на поместувања во X правец. На овој слайд можат да се видат резултатите од овој нумерички модел во споредба со експерименталните тестови, и ова е конкретно за дамперот со една плоча, и може да се забележи дека точноста, дека е поклопувањето на овие резултати е доста голема, и корисно во овој модел е тоа што моделот е едноставен и може лесно да се применува за масовна употреба. Целата суштина е доаѓање на правите вредности на параметри за употреба на овој Максвелов модел, кој што со овие резултати се потврдува дека се доволно задоволителни, повеќе од задоволителни. И на наредниот слайд се прикажани резултатите за дамперот со две плочи, и исто може да се заклучи истата корелација. Како заклучок можам да изнесам дека експерименталните резултати се совпаѓаат со нумеричките анализи со помош на експоненцијалниот Максвелов модел и исто така може да се увиди точноста на овие резултати и преку компарацијата на дамперот со една плоча во однос на дамперот со две плочи според нивниот сооднос на параметрите во однос на крутоста и на придушувањето. И исто така важен заклучок од ова е дека со едноставен модел може да се направи голема промена за употреба на овие системи, општо е за пасивни системи за контрола на вибрации, за помодерно сеизмичко проектирање во иднина. Ви благодарам.
Благодарам, Маја. Секогаш аналитичката потврда на експериментални резултати е значајна, бидејќи овозможува понатамошна примена, па со оглед на тоа, претпоставам дека ќе продолжуваш и понатаму во докторските истражувања. И благодарам и на тебе и на сите што навистина бевме во рамки на предвиденото време. За кратко време се кажа многу важни работи, многу важни истражувања и сите сме побогати за некои нови сознанија. Со тоа јас мислам да ја завршиме оваа сесија. Дури пред времето можеби малку, но тоа не значи дека не може да уживаме малку порано и со кафе паузата. Благодарам да сите.